So our speaker for the colloquium today is Izzet Coskun. He's professor at UIC, where he's been since 2013. Before that, he was a Moore instructor at MIT, and he got his PhD from Harvard. So Izzet is an algebraic geometer who's done work in all kind of aspects of that vast subject, from combinatorial algebraic geometry and Schubert calculus to birational geometry of moduli spaces and algebraic dynamics. He's published over 50 papers, many awards, and he's also a very generous mentor, formally of about a dozen or more PhD students and postdocs, and informally of many more young people who've had the good fortune to talk math with him. So without saying too much more, I want to turn it over to Izzet, who will tell us about points in the projective plane.
Well, thank you very much for the invitation and for the very nice introduction, and for everyone for being here. So today I want to tell you a little bit about points in the projective plane. So let me just start with sort of what's underlying this. So start with the space, any space you want. For us, this will usually be a compact, complex manifold, as a submanifold of projective space typically. But you can think of this much more generally. Say that you have some space, right? And then you can associate it to that space. You can talk about the configurations of M points on that space. So what is that? So here is my cartoon of my space X. Let me just also outline it, since you can't see my hand gestures. And what you do is you just take M unordered tuples of distinct points on the space. And then, most of us encounter a version of the space at some point, whether you're studying braid groups or, secant planes to a manifold, or, whether you're doing algebraic geometry. Many of us encounter this kind of, a space with like M tuples of points on this, okay? And then somehow we want to understand the geometry of the space. The immediate problem that you see with this is that it's not compact. The problem is that even if X is compact, right, the space is not compact, because what can happen is that if you have two distinct points, let me see whether I can sort of, what can happen is that they can collide, right? And then the way we define this is we are not allowing points to collide, so that, they're as the points are approaching to each other, then there won't be a limit. All right, and then the first problem that you run into is that how do you compactify the space? All right, so there's a naive way of compactifying the space, and this is known as the symmetric product. So what do? What you can do is you can take your space and take M copies of the space. So that you take X cross S, X M times, right? And now you see, if you take this, then the symmetric group acts on this, right? So if you think of the coordinates of this thing as x1 ... xm, the symmetric group acts on this by permuting the coordinates. Yeah, and then the symmetric product is the quotient of the product by this action of the symmetric group. So if X is compact, now this is a nice compact space, right? And then if the dimension of X is 1, then this is a beautiful, nice space. And we understand this geometry fairly well, especially if the number of points is large, then we completely understand the topology and most of the geometry of the space. So let me do an example so that you see what can happen. So let me take the Riemann sphere, okay, or complex projective line, right? And say that you have on the sphere M points, here are my points, right? So, okay, I can write down the coordinates of these things of x1, y1, ... xm, ym of my M points, right? So there's a way of thinking about it. So instead of thinking about the points, what I can do is I can think about the polynomial that vanishes on these points. And then, up to scaling, you can write this thing down, right? So if my variables are x and y, so you write xyi minus yxi, right? So that this, and take the product from I equals 1 to m, right? And if you do that, right, you get the polynomial that vanishes on these m points. And then, as I said, this polynomial is determined up to scaling. Of course, if I scale everything, then you don't change the roots by a non-zero constant, and you don't change the roots, right? So then you see you get a nice duality between the roots of the polynomial and the coefficients of the polynomial up to scaling. And if you think about what that means is that, how many coefficients does this polynomial have? So, this looks like a to the m, x to the m, plus a to the m minus 1, x to the m minus 1y plus a naught y to the m, right? There are m plus 1 coefficients here, and they're determined up to scaling, and they're not all allowed to be 0. So the way you see is that what you get is complex projective space of dimension m. So in other words, the symmetric product, as I claimed, is a really nice space, and in this case, you can completely understand that it's complex projective space of dimension m. All right. Okay, so then why am I even talking about this problem? The problem is that if the dimension of x is at least 2, I see that I'm going to keep going between m and n. So if the dimension of x is at least 2, then the symmetric product is singular. Yeah. So what happens is that, when the points collide, when you identify them, you get the singular locus. And that's not, as a general rule, we prefer to work with smooth spaces. So then what we're going to do is we want to do something about it. We don't want to deal with singular spaces. All right, so then in comes Grothendieck. And Grothendieck had a really nice idea that was very influential in geometry. So he said that instead of looking at the configuration space, right? So let's go back our example of P1. Instead of looking at the m points on P1, let's instead think of polynomials that vanish on these points. And again, I can do this because, secretly, as I said from the beginning, my x is some projective variety or complex projective manifold, right? So what I can do is, instead of looking at the set configurations of m points on the space, let me look at polynomials that vanish on those points. I mean, of course, if you have m distinct points, right? And then, you give all the polynomials that vanish on those points, and then you can recover the points from the polynomials so that you don't, you don't get anything vastly different. But, the interesting thing happens is when these points start colliding. So let's see what Grothendieck says. So instead of looking at the points, look instead at the polynomials that vanish on these points. These polynomials form an ideal. And you see, these ideals have various invariants. Like, for instance, they have an invariant called like the Hilbert polynomial, right? For instance, what's the dimension of the space of degree d polynomials that vanish on these points? So that dimension you can keep track of, right? So that's an invariant of this ideal, right? And then, so what he says is, instead of forget about the points, look at these ideals and instead parameterize these ideals. And you can do this thing more generally. You don't just have to restrict yourself to points, and then it leads to some space called the Hilbert scheme. And there's a big theory of this thing, but we are not going to get too much into this except when we are talking about points, right? And then the configuration space naturally sits on this Hilbert scheme, and I'll denote it like this. So remember that the symmetric product was denoted like this with round parentheses. So this is with brackets. So when it's with brackets, there will be this Hilbert scheme, which you should think of as parameterizing these ideals vanishing on m points. Okay. So before I go further, maybe I should explain, at least give you some examples of like, how does the symmetric product in this Hilbert scheme differ? Like, what's the difference? So let's try to understand it, at least in a few small examples. Any questions so far? By the way, if you have any questions or any comments, you should just hop in. Unmute yourself and say it, okay? So let's understand sort of a little bit the difference between the Hilbert scheme and the symmetric product. So let me just take C2 because it's easier to write down the equations, and then I want to understand the Hilbert scheme of 2 points on C2. All right, so if you have two distinct points, say like something like 0, 0, and 1, 0, then I can write down the polynomials that vanish on this. It's not so hard, right? So y is always 0, and x is either 0 or 1. Yeah, so that you can write down the polynomials. And then, this invariant that you want is really the dimension of the polynomial ring modulo the ideal. In this case, you can see that this is 2, right? Corresponding to the fact that we have 2 points, because this as a basis, you can take to 1 and x to be a basis of this quotient, for instance. So there's not much that's surprising. And if you had 2 points, then you would be able to write the line between them and the quadratic equation in that line that gives you the 2 points, right, in general. And then this dimension would be 2, and you would be able to write down the ideal. But now what happens if the points collide? You see, if the points collide, you see I can write the ideal something like this: y squared equals x minus ay. And I claim that this is fine because this is, I can again compute this dimension, right? If I look at the polynomial ring modulo I, right, then I can take my basis to be either 1 and x or 1 and y, right? And y squared is already killed. And then, if I put x or y, then I can solve for the other one from this linear relation. But you see, if I was just looking at the symmetric product, right, then the 2 points become the same. And then, all you remember is that you have a point with multiplicity 2. But you see that the Hilbert scheme already remembers more information, right? Because as I change this A, right, I get different ideals. They're not the same ideals. And then, you can sort of draw a little cartoon of this thing as, a point together with a little tangent direction, where the tangent direction is telling you what the slope of that line is. That's defining this ideal. Okay, so there you see that already this Hilbert scheme is remembering a little bit more information than the symmetric product. It's the symmetric product only knows that this is a point with multiplicity 2, but the Hilbert scheme associates some sort of tangent vector to that point. Okay. In general, it turns out that if you want to understand the Hilbert scheme of 2 points, that's not so complicated. It's just a blow-up of the diagonal in the symmetric product. And here the dimension and whatever doesn't matter. So it becomes just a desingularization of the symmetric product. So let's look at, to just get a little bit more of the flavor, I think what we should do is we should also look at 3 points, so that, and again, there can be aspects. So again, let me take C2 so that I can write down the equation. You see, when you write down your ideals, these ideals can reflect both the global geometry and then the local geometry can come into the picture too. So let's see some examples. First of all, I can take 3 random points like 0, 1, 0, 0, and 1, 0 in C2, right? And then you can write down the equations of this thing with not too much difficulty, right? X times y is always 0. And then either x is equal to 0 or 1, or y is equal to 0 or 1. So that you see that you can write down the equations like this. And again, if you looked at this dimension, the polynomial ring modulo the ideal, it would be 3 spanned by 1 x and y if you want, right? Because this solves for y squared, this solves for x squared once you have x and y, and this gives you xy. Okay. Now you see what happens if the points were, for instance, collinear. So let's look at that, right? So if I make the points collinear, then you see that the shape of the ideal changes a little bit. Say that I take the points 0, 0, 1, 0, and 2, 0, right? Then you see that y is always 0. So I have y as a generator. And then I need to decide, and then x has to be 0, 1, or 2. So you can write it as x minus 1 and x minus 2. Okay? I mean, I'm not really proving for you that these really generate the ideal, but you can easily convince yourself that they generate the ideal. It's not so hard to do, okay? And again, you see that here the dimension to polynomial ring modulo this ideal is 3, and this gives you a basis. And then, maybe I should stop and point out that you should appreciate Grothendieck's theorem at this point, because you see, I mean, how does Grothendieck prove this theorem that, all these ideals fit into some sort of reasonable space. I mean, what he does is, of course, I mean, you know, there's a natural way of doing that, right? You write down the generators of the ideal, and then you hope that you can move the coefficients of these generators, right? But you see that like the generators of the ideal already can look vastly different depending on the positions of the points, right? So what actually Grothendieck does is that says that forget about the generators, take degree d polynomials for some d large enough vanishing on your points. And then he says that the shape of those degree d polynomials always look the same for if d is sufficiently large, no matter what ideal you have. And then you can vary the coefficients of those. So that's how this thing works, okay? But anyway, so these are okay, but like for us, maybe the more interesting question is that how do we understand when these 3 points collide? So let's see a few examples when the 3 points collide, right? So one thing that I can do is I can write this. I can do x cubed times y minus ax minus bx squared, right? So if I do this and look at cxy mod I, this again has dimension 3, and you see that it has basis 1x and x squared. These kinds of things are called curvilinear. The reason why you call them curvilinear is because they lie on the smooth curve. So, you know, if you look at y minus ax minus bx squared, this is some smooth parabola to that point. And then you see you draw it like as representing a little piece of the parabola. Of course, as the degree of this thing gets, these things become more and more cartoonish. But, you know, at least in this case, you can pretend that I've drawn a parabola. But anyway, so these things are called curvilinear because they lie on this smooth curve, right? But you see, there can be other more complicated things. So here's another thing that you can have, like you can have the ideal generated by x squared, xy, and y squared, right? Cxy mod I also has dimension 3 now with basis 1, x, and y. So this is slightly different in that it doesn't lie on any smooth curve, right? So you can compute, so to speak, the tangent space to this ideal, and then, you know, the derivatives are, you know, you can compute the tangent space, and then you see that it's really the whole of C2 at that point. So that's, you know, it doesn't really lie on any smooth curves. It turns out that when you have 3 points, these are the only possibilities. But as you can imagine, as you increase the number of points, again, you know, if in the symmetric product, if you had 3 of the points collide, all you would remember is that, you know, you have a point together with multiplicity 3. But you see that in the Hilbert scheme, you just remember a lot more information. Like, you know, there's this, you know, if they're curvilinear, you remember a piece of the parabola that they lie on, so to speak. Yeah. And then, as you can imagine, already for you know, 3 points, the picture is getting a little bit complicated, right? And then if you increase 3 to make m, then you would think that it gets vastly more complicated, and yours would sort of be right, yeah? For instance, like, you know, there is an easy generalization with this example. Say that you look at the ideal x to the m and y minus, you know, a1x plus a2x squared am minus 1 x to the m minus 1. Again, these things are called curvilinear because they lie on the smooth curve, right? And, you know, the dimension of this thing is m, and it has a basis given by 1x xm minus 1. All right, so there is a big miracle that really happens when the dimension is 2, and there are 2 really nice theorems. So let me tell you what these theorems are. Okay, there are 2 really nice theorems. So the first theorem is due to Fogarty back in the 70s, and it says the following thing. Suppose you have a smooth surface. So the dimension of x is 2, complex dimension is 2. Then it says that this Hilbert scheme of points is a smooth, irreducible 2m dimensional manifold. Okay, so it's this beautiful space. It's, you know, it's a projective manifold of dimension 2m, And furthermore, it has this property that it maps to the symmetric product. And how does it map to the symmetric product? It maps to the symmetric product the way you would think it does, right? So if you have a scheme like this, say that you have some sort of scheme, so then, it could be like every little parabola there, a little bit hyperbola there, maybe a few distinct points or something like this. What you do is you just take the points counted with multiplicity. And that gives you a point at the symmetric product. And it turns out that that's a nice, well-defined morphism, yeah. And it has a name. It's called the Hilbert Chamorphism. And what it is that it's a resolution of singularities. Okay, I mean, it has many other properties. For instance, this resolution of singularities is very special in that the Jacobian of the map, the Jacobian does not vanish in this thing. So this thing is called the Crepin resolution, for instance. So, it has very nice properties and it's been studied a lot, but, let me not get into those things. All you need to know that this Hilbert scheme, when the dimension is 2, is really, really nice. And, it gives you this Hilbert scheme as some smooth manifold of dimension 2n. And similarly, you see there is a theorem again of Briançon this time. So I think from the early 80s, which says the following thing. Again, suppose that I have a smooth surface, right? Then you can ask how complicated can the points supported can points of this Hilbert scheme supported at one point be, right? So you look at these things supported at one point, we already saw that they can be somewhat complicated, right? There are all these curvilinear things depending on these m-1 parameters, right? These AIs, right? So already something supported at one point can depend on these m-1 parameters. The theorem of Briançon tells you that actually the locus of things supported at just one point is irreducible and of dimension m-1 and contains these curvilinear schemes as a dense open set. So, there are other things on the boundary, but this is most of it. Okay, so so that we can pretend that we understand most of the points. So in particular, you see the boundary. So if you look at the configuration space, and look at the complement of the configuration space in this Hilbert scheme is a nice irreducible divisor that I'll call this boundary divisor B. Okay. All right. So far from what I've said, you really need to take 3 things out of it. The first thing is that, when the dimension is 2, the Hilbert scheme of points gives a very nice compactification of the configuration space, which is smooth, irreducible. And then, the complement of the configuration space is an irreducible codimension 1 set. Okay. So these are the main takeaways from this thing, and you should think of the Hilbert scheme as a resolution of singularities, and this happens in dimension 2. So let me just make a quick aside, okay? You might wonder what happens if the dimension is bigger than 2. So if the dimension is bigger than 2, then the Hilbert scheme can be pretty awful. So it doesn't solve the problem of the singularizing symmetric product. Let me give you a cute example of Yarabino from the 90s. So here is what you can do. So this is going to be 96 points on C3, okay? So we look at the Hilbert scheme of 96 points on C3, and here is what you do. Let me give you an ideal like this that will be in the space. So what you do is you take all monomials of degree 8. So, things like x to the 8, y to the 8, z to the 8, x, y, z to the 6, whatever you can think of. You put them all in, okay? And then you take a 24-dimensional subspace of homogeneous polynomials of degree 7. I mean, I don't care what subspace you take, but you take a 24-dimensional subspace of such things, okay? And you look at the ideal generated by these things. Then I claim that this should be a point in the space of, ideals of length 96 that is parameterized by this Hilbert scheme. So let's count. So if I look at the polynomial ring modulo the ideal, right? So I killed everything of degree 8 or more, but I haven't touched things with constants degree 1, degree 2, degree 3, degree 4, degree 5, and degree 6 polynomials. And I've only killed the 24-dimensional subspace of polynomials with degree 7. So now we can count. So there's one constant. There are 3 linear terms, x, y, z. There are 6 quadratic terms, x squared, y squared, z squared, x, y, x, z, y, z, whatever. So it's always a triangular number. There are 10 cubic forms, 15 quartic degree 4 forms, 21 degree 5 forms, 28 degree 6 forms, and there are 36 degree 7 forms, except that I killed the 24-dimensional subspace of them. So I have 12 left over. And if you sum them up and if I did it correctly, you get 96. Okay? So then you see that you have ideals like this in that space. Okay, that's good. But let's see how many such ideals you get. So what does this data depend on? This data depends on this choice of vector space, right? Homogeneous polynomials at degree 7 and 3 variables is a 36-dimensional vector space. So of this 36-dimensional vector space, you are choosing this 24-dimensional subspace. This kind of thing is parameterized by something called the Grassmannian. It doesn't matter what this is. All you need to know is that this dimension is 288. Okay, so there's a 288-dimensional space of things, right, of the form I that's supported at the origin. But you see, nobody is telling me that I should put this I at the origin. I could move it to any point of C3 as well. So I could also move this point. So altogether, you have a 291-dimensional space of such ideals, right? Because I can move the origin to any point of C3, okay? But now at this point, you should say, wait a minute. The configuration space, I can count what the dimension is, right? A C3 to the 96 divided by the symmetric group, right? C3 to the 96 has the dimension 3 times 96, 288. And now at this point, you should say that, wait a minute, this is bigger than that. How did that happen? What this example says is that you can have, schemes of length 96 supported at the origin that are not limits of 96 distinct points. This didn't happen in dimension 2, but already in dimension 3, these kinds of things happen, right? So what this is saying is that this Hilbert scheme can have many components, some of more than expected dimension. In fact, you can even make components of less than the expected dimension too. But what this is saying is that the geometry of these Hilbert schemes, when the dimension of the underlying space gets larger, can be a mess. So that's why we stick to surfaces. Okay. So that was an aside. So all right. So let me go back to my theorems to remind you, when my dimension is 2, life is miraculously wonderful, right? So this Hilbert scheme is a smooth projective manifold of dimension 2m. It's the resolution of singularities of the symmetric product, and this boundary, the complement of the configuration space, is an irreducible codimension 1 set. All right, so we are golden. Now you see we can ask all sorts of questions. So whenever you have a nice moduli space, then it leads to lots of beautiful mathematics. So, and then, some of the basic questions that you can ask, okay, you have some abstract space. How can you possibly embed it in projective space? So what are the possible embeddings? Or more generally, you can ask, like, what are the rational maps from this Hilbert scheme to projective space? Or you can ask, can we get other compactifications of this configuration space? Okay, the Hilbert scheme gives this one, the symmetric product gives this one, but are there? Yeah.
Can I interrupt and ask a question? X
Sure.
is a surface here or
X
not?
is a surface.
Yeah. X is still a surface. Okay,
From
thank you.
now on, let me say it like this. Let's write it down. From now on, X is a surface. And in fact, X will be P2 for the purposes of this talk. I mean, a lot of what I'm going to talk about, you can do on other surfaces, but I mean, I'm not going to talk about it here. Okay. All right. You can ask all these kinds of questions. And as I said here, I'm going to concentrate on P2. Okay. And I'm going to sort of try to phrase some of these questions as like, what are special configurations of points on P2 on the plane so that we can visualize. I mean, one of the nice things about the subject is that you can visualize some of these things to a certain extent. All right. So, so let's understand a little bit of, okay. So here is what we should say. So let me just maybe quickly explain. You see, if you have an embedding of any space really into projective space, then you can look at hyperplane sections of your space. Yeah, and these things give you codimension 1 things in your space. The terminology for this thing is divisors, right? And you can try to understand the geometry of these divisors, and that tells you a lot about like what are the possible maps that you get from your space to projective space, and when you get an embedding and things like this, right? So as I said, I'm going to concentrate on P2. There are 2 special divisors on this Hilbert scheme already, 2 very special codimension 1 sets that we've essentially seen. So let me make them more precise. The first thing that you can do is already seen the boundary divisor. So this is the complement of the configuration space, like the locus of schemes that are not M distinct points. So the complement of the configuration space, so we have this boundary divisor, right? And then the other thing that we said is that we have this map to the symmetric product, which, let me remind you again, what you do is you take this scheme that you have, you just look at the support and you count it with multiplicity, okay? Or you take the 0 locus of this ideal and then you count the points with multiplicity. All right. So you see, here is another kind of divisor that you can define. So again, we are working on P2. Let me fix a line. Fix a line L. And then you see what you can do is you can ask for the, for the ideals that have a point for this, you can ask for schemes that have a point that lie on L. Okay. So then this is codimension 1, because the way you can think about it is that, these n-1 points, these n-1 points are totally free, right? So they have 2m-2 freedoms, except that this last point is sort of stuck on L. So it has only 1 freedom instead of 2 freedoms. So that you see that its dimension is 2m-1 instead of 2m. So it's codimension 1. And I'll denote this thing by h. Yeah. So it's a nice theorem. It's a nice theorem of Fogarty. Again, many of these theorems hold more generally on arbitrary surfaces, but I'm just telling you the answer for P2. It says that any codimension 1 subvariety, or the class, maybe I should say, the class of any codimension 1 subvariety is a linear combination of these, where A and B are integers. Okay. And if you're working over the rational numbers or something, maybe that's a better thing to do. Then you don't have to worry about this over 2. That's a technical point. Okay. But so what this is saying is that any divisor, the class of any divisor is a linear combination of these. So then you see, you can ask this question more like, we can make some of these questions a little bit more concrete. So if I'm talking about possible embeddings, right? If you have an embedding, then you can look at the hyperplane section, and then you can ask what combinations of H and B can be the hyperplane sections of embeddings. All right, so that's one kind of question you can ask. When can D be the hyperplane section under an embedding? Yeah, so what conditions for what A and B? Right, and then the other question that you can ask is when is this D effective, in the sense that, if you take a random linear combination of these things, there might not be a codimension 1 subvariety that represents that class, right? The question is, for which A and B is it the case that this D is the class of an actual codimension 1 subvariety? Okay. You can ask that thing, since this is a 2-dimensional space, right? I mean, the way you should think about this is that, both of these things are cones, convex cones like this. The way you should think about this is that if I have an effective, if I have an effective thing with this class and another effective thing with that class, right? Then I can take any linear combination and then say, take the union of these things, appropriate union of these things, then I can represent anything, up to taking, integer multiples, then I can represent anything in between as well. So that you see, the question that you really want to know is what are the extremal ones? That's the real question that you ask. Okay, so if you want to make this thing a little bit more concrete, so that it doesn't use much jargon, is that, what is the most special codimension 1 configuration of points in the plane? Okay, we'll do some examples of this. There is one obvious answer to this thing, right? This B is certainly pretty special, right? Most of the time, if you have M points, they are distinct M points. So 2 of them are colliding. That's pretty special. Okay, that's pretty special, or it's also not that interesting. It doesn't depend on M, and we understand it. So in other words, what this is saying is that if you want to answer the first question, when is D effective? One extremal ray of that thing is B, right? The question is, what is the other extremal ray? That's what we're going to ask. Okay. So let me give you a few ways of viewing things. So let's just do this. So here is what I can do. Suppose that you have your points, right? Or your scheme Z, as we've been saying, right? So then I can do the following thing. I can look at polynomials of degree n that vanish on Z. This is some vector space, right? If I look at the, if you have M distinct points, right? You generally expect this to be a codimension M linear space in the space of polynomials of degree n, because, each time you have a polynomial, so let's write it down. So, maybe this thing looks like xi, y, j, z, d minus I minus j, a, I, j, right? So if I have a point and plug it in my x, y, and z, I get a linear equation in the coefficients of this polynomial, right? And if you have M points, then it's M linear equations. And, as we teach our linear algebra kids, right? If you have M linear equations, then that's a codimension M linear space, at least most of the time, if the rank of the matrix is full, right? But most of the time, you would expect that the rank of the matrix is full so that you get a codimension M linear space, right? So that you see what you can do is you can look at polynomials of degree n vanishing on Z. This is always a subspace, typically of codimension M, of polynomials of degree n, right? So what that means is that you get a map from this space into what's called the Grassmannian, which just parameterizes, polynomials of vector spaces of codimension M in this vector space, which happens to have dimension m plus 2 choose 2, okay? And then what you can do, of course, this way you can get interesting rational maps. This thing does not have to be defined always. So the problem is that the dimension of this can jump around. Meaning that the matrix that you get by putting these M points might not have full rank. Right? So just to give you an example of such something like this, suppose that you have 4 points in the plane, right? And then you talk about polynomials at degree 2. If you have polynomials at degree 2, that's a 6-dimensional vector space. If it's going to vanish on 4 points, typically there are a 2-dimensional vector space at degree 2 polynomials vanishing on 4 points. But suppose that the 4 points are collinear. So if the 4 points are collinear, now you see if you have a degree 2 polynomial vanishing on those 4 points, it has to be identically 0 on that line. But, there are a 3-dimensional, say that this thing is X, right? So then, there is a 3-dimensional space of polynomials degree 2 vanishing, say that line is X equals 0. There's the 3-dimensional vector space of polynomials degree 2 that vanish on those 4 points. And, you can check without much difficulty that when you have 4 points, they fail to impose independent conditions on degree 2 polynomials if and only if they're collinear. But you see that when it's collinear, the dimension of this vector space jumps, so that's why you don't typically get a morphism. It is a fact, though, that if you have polynomials at degree m-1 or more, okay, then m points always impose independent conditions on polynomials at degree m-1 or more. This is something that you can check, but I'm not going to do it. So that you see, in particular, when this n is bigger than or equal to m, it's not just the rational map anymore. You get a morphism in that case. Okay, so then you see this gives you so for instance, this is enough already to characterize all the divisors that can be realized as hyperplane sections of embeddings. And it turns out that, you know, you can compute these things. This map is when n is equal to m-1, you get the extremal map. So, you know, it's not an embedding in that case. It does contract like this locus of points that lie on a fixed line, m points that lie on a fixed line. And from there, you can conclude that, you know, anything that's the hyperplane section by an embedding has to lie in this cone. And that's precisely the cone in which that they can lie. Anyway, but the more interesting question that I want to concentrate on is that what are the codimension 1 special configuration of points in the plane? All right, so now everybody should be able to answer the first few. So if I have 3 points, what is the codimension 1 special configuration that they can lie at? I don't know, maybe I should call on people.
They are lying on the same line.
Yeah, they can lie on a line, right? So like, you know, the 3 points typically won't be collinear, right? Here are 3 points that are not collinear, right? But in codimension 1, they'll be collinear, right? Because 2 of the points will determine a line. And to say that the 3rd point has to lie on that line means that this 3rd point is not free, but has to lie on that line. So you see that's the codimension 1 condition, okay? So collinear points. And you see that's extremal. You can't have anything more special than that in codimension 1. And you might wonder, how on earth do you check something like this? Here is what you can do. Yeah. Suppose that you have a codimension 1 configuration. Say that you look at this thing and say that you ask there's some sort of codimension 1 thing that's effective. Yeah. Okay. So now you see, if you have an effective codimension 1 thing, then you can intersect it with irreducible curves. Say that I intersected with an irreducible curve. So, you know, these are complex manifolds, so everything is oriented. If the curve is not contained in this divisor, right, then it can only intersect it in finitely many points, possibly 0. So that you see that it has to be like this, right? But you see, the danger is that the curve could be contained in D. Right, then we cannot say, I mean, then the intersection numbers are complicated things, right? So you see that D dot C has to be greater than or equal to 0 unless C is contained in D. Then I don't know what happens, you know, then this is a complicated question, right? So in particular, you see that if I can give you curves that move around a lot, right? In other words, if they mostly cover most of your space, right? Then it can't be that the C is contained in this D, so that the intersection number has to be greater than or equal to 0, okay? And you see we have such a thing in this case. So let me draw a picture. So here is your P2. Let me take a conic. So this is a conic. Yeah, so given like something like y squared minus xz equals 0, right? And let me take 3 points on this. And then, you know, vary these 3 points on this fixed conic any which way you want. Right? Those 3 points never become collinear. Because if they ever became collinear, then the line that they span would have to intersect this conic in 3 points, right? And, you know, that would be bad because Bezout says that they can only intersect in 2 points. Yeah, so that you see that, and then you see if you have any 3 random points that are not collinear, you have a conic like this that contains them. so that you see that the curves that you get by, say, moving one of these points around, right, cover the space and have to have the property that d dot c has to be greater than or equal to 0. But you see, since these never become collinear, this curve C, let's call it, C dot the locus of collinear points is 0. So that you see that that's extremal. You can't do better than that. Okay? Well, now you see we can keep going. So let's keep going. Suppose that now I look at 6 points. What can you do when you have 6 points? The hint is that there is a...
Lying on the conic.
Right, I can ask that the 6 points lie in a conic, right? Typically 5 points determine the unique conic, right? So the 6 point is not going to lie in the conic, but in codimension 1, it lies in the conic. And again, this is extremal by a similar argument. Okay, and you can keep going. So suppose that now you have any triangular number, say that you have 10 points, then what do you do?
Cubic.
So you lie on a cubic, and if you have 15 points, you lie on a quartic, and so on and so forth. So if you have a triangular number of points, then it's pretty easy to see what the extremal configuration, like what's the most special configuration of points is. And that's simply that they should lie, they should lie on the curve of degree d. If this m is d plus 2, choose 2, then they should lie on a curve of degree d. So that's the generalization of collinear points. The first time this problem becomes interesting is when you have 12 points. So now I want some guesses as to what you think the most special codimension 1 configuration of 12 points is. We need to have some wrong guesses, otherwise it's not so good. I mean,
Put them on an intersection of 2 curves.
All right, I could try that. For instance, like you can ask that you put them, for instance, on the cubic and the quartic or something like this. But even before that, suppose that I put them on the cubic. Yeah. You see, the problem with that is that it's not a codimension 1 condition, because 9 of the points determine the cubic, right? So to say that the remaining 3 points lie on the cubic is codimension 3. It's not codimension 1. Okay? But that's a good guess. That was my first guess too. I mean, it turns out that it's not so easy to guess what the answer is. So let me maybe tell you the answer. And it's the following thing. So you see, I can take the tangent bundle of P2. Okay, the tangent bundle of P2, right, is a vector bundle of rank 2. Yeah, and the point is that suppose that I twist it by 2. Okay, so now what does it mean that you twist it by? So the way you should think about this is that the sections of this thing are, degree 2 polynomial valued vector fields, if whatever that makes sense. But in particular, we can compute the global sections of this thing, like how many global sections there are. There's something called the Euler sequence. So if I twist it by 2, it looks like this. Okay, and then the point is that the dimension of the global sections of this is 24. Okay, now you see this is a rank 2 bundle. So to say that a section vanishes should be 2 conditions at a point, because this is a 2-dimensional vector space, and to say you make it 0, it should be 2 conditions. And there are 24 sections, right? Typically, if you have 12 points, you would think that a section that vanishes at those 12 points should just be 0. Okay, so it turns out that in this case, the most special configuration of points is like this. It's the set of points Z such that they fail to impose independent conditions. on sections of this bundle. And this wouldn't be the first thing that you would have guessed for most people, I don't think. Okay. And then you see, if we go back, right, these were already of this form. So like, you know, if you look at lines, right, lines are sections of a line bundle that's called of one.
I think we lost Izzet.